All of these are equal to 0. Now, what does this mean? Okay? What does this mean? This means that integrand is 0. Now, an integral can be 0 because of the two reasons. It can be more than two reasons, but there are two basic reasons. One is limits, other is the integrand is 0. Okay? Now, if the integrand is non-negative, it is not negative actually. Okay? It's non-negative and it's equal to 0, then integrand must be 0 actually. Okay? Or you can also write this as that this is equal to t times t minus 1 square times h of t and the norm of it square, and this norm is L2 norm. And what do you mean by L2 norm? If you remember, so the inner product, what is the meaning of norm? F square, it means that inner product of f with f actually. And what would be the inner product of f with f? By this definition is going to be 0 to 1 f of t multiplied by f of t, any f of t ka square dt. So this is really the L2 norm. So if I have f of t ka square dt, this is equal to the magnitude of, what do you call, the norm of f square. So we not going to have squares here, we're going to have this actually. So t times h of t square in L2 norm is 0. And if the norm of something is 0, then we proved one properties of the norm in the 4th chapter, that if the norm of some vector is 0, if and only if the vector itself is 0. Okay? So the only vector that has norm 0 is 0 actually. So if the norm of this guy is 0, that means that t times t minus 1 h of t equal to 0. Now here is the case actually. Okay? Here is the case. Here is the case. Now if you take a t between 0 to 1 and their product, okay? So if the product of this is 0, then you have three possibilities, either t equal to 0 or t minus 1 equal to 0 or h of t equal to 0. T and t minus r are abstract instants between 0 and 1. So we can't assume them equal to 0 or equal to 1. So the only possibility is that h of t is 0. H of t is 0. Now here is the case. Okay, which implies that h of t is 0. And if the h of t is 0, then we have the following trouble. What is the trouble? The trouble is this. I'm going to use this identity. Which identity? This identity. This identity. What does this identity shows? This identity shows that f of 1 minus f of 0, f of 1 minus f of 0 is equal to 0 to 1 f of t times h of t bar dt equal to 0. So I'm using this identity here again. And keep in view, up to this time, we haven't have any assumptions on f actually. So the f is general. Okay, so the f is general. Here we assumed f to be concrete. So if I'm using this notion where h is 0, what does this mean? This means you have this. Okay? And once you have this, because h is 0, the thing that you conclude is that for any polynomial f, because f is arbitrary polynomial, f of 1 minus f of 0, this is equal to 0. Keep in view, from these calculations, by choosing the particular, what do you call, f, I have determined h actually. Okay? But this h is going to satisfy, so this h and any f are always going to satisfy this condition actually. Okay? They are always going to satisfy this condition. So what I did, I substituted the value of h in this expression. So you're going to get f of 1 minus f of 0, f of 1 minus f of 0 equal to 0. Where f is any polynomial. For all f in P, no restriction. But this is not true. Is it necessary that every single polynomial should give you f of 1 minus f of 0 equal to 0? The answer is no. This is a contradiction. This is contradiction. Why? Contradiction. Because if you take any f, say you take f of t equal to t, simple polynomial actually, simple polynomial. This does not satisfy f of 1 minus f of 0 is not equal to 0 actually. Is not equal to 0, and hence this is a contradiction actually. This is a contradiction. So let me just quickly go through the proof again. So we took G and I computed the inner product of TF with G. So it turns out this is equal to f prime of x by fundamental theorem of calculus. It is f of 1 minus f of 0. So f of 1 minus f of 0 is equal to this, but t star is the adjoint of it, so it's going to be f t star g, but t star g has been given the name h. So if you compute this, you're going to get f of t times f of h bar. So in order to determine h bar, I'm choosing, now this identity, I'm emphasizing on this fact actually, that this identity is true for all f in the polynomial, no matter what polynomial you have. H is fixed, but not f. F is arbitrary. H is fixed, f is arbitrary. The question is, can I find h? The answer is yes, I can play cleverly. If I choose this f and substitute into the formula, I'm going to get what you call h equal to 0. So if h is 0, and I substitute my h equal to 0 here, I'm going to get f of 1 minus f of 0 equal to 0. And this must be true, this identity must be true. Since this is true for all p, this should also be true for all f in the space of the polynomials actually. And if this is true for all space of the polynomial, that is a contradiction. Why? Because it is not necessary that every single polynomial should satisfy this condition. Just take this simple polynomial f of t equal to t. So you're going to get f of 1 minus f of 0 does not equal to 0, and hence you have a contradiction actually. And this contradiction is coming due to what? This contradiction is coming due to this fact that you have assumed that t has an adjoint t star actually. So what does all these calculations shows? That t does not necessarily have a self-adjoint. Every single operator does not necessarily have an adjoint actually. Okay? Does not necessarily have an adjoint. Okay. So let's move on ahead a little bit more. So in order to make sense of it, I'm just giving you a view. In order to make sense of it in detail, you have to read the book actually. This is important, that you have to read the book. Try to make sense of things from here and then read the book, then every single thing in the book, would make sense to you. Okay? The only way to do here, unfortunately in this mode, I'm speaking and, with an empty class where no one is listening. So, I'm assuming that everyone understands it actually. But we're going to have Zoom sessions where you can ask the questions. But these discussions are going to help you to make sense of the stuff that you have in the book. Okay? This is an important thing. Alright. Here is an important theorem. Okay? So with previous example we saw some operators have adjoint and some operators do not have adjoint. So here is an interesting theorem that says that if you are in finite dimension, you always have an adjoint actually. So any finite dimensional linear operator has an adjoint. Okay? And obviously this is going to come from the fact that every linear transformation between the finite dimensional vector spaces has a matrix, and corresponding to a matrix we can find an adjoint actually. Anyway, so here's the theorem. So let V and W be inner product spaces, okay, on same field, and let T is a linear transformation from V to W. Let beta V1, V2, Vn, and gamma W1, W2, Wm be the orthonormal basis. So this is a bit different from the previous theorem that we did, where we didn't have an assumption on B. The B was just B, bases, and gamma was orthonormal basis. But now I will prove the theorem under the assumption that beta and gamma both are the orthonormal bases of V and W respectively. So these are the orthonormal bases of V and W respectively. Okay. Then there are 2 points. Number one, T has a self-adjoint, as a self T has an adjoint. T has an adjoint operator, always T star. Okay. And secondly, you can ask an interesting question: how the beta gamma representation of T and the beta gamma representation of T star are related with each other. So the second part gives the answer that if you want to compute the beta gamma representation of T star, okay, beta gamma representation of T star, and the order is important. So what you can do is that, so it's gamma beta representation of T star, then what you can do, take the beta gamma representation of T, okay, and the gamma beta representation of T, okay, and compute its conjugate. So I know that a linear transformation can completely be determined through what do you call its matrix actually. Okay, so if you know the matrix representation of the linear transformation T, take its conjugate, you're gonna get the matrix representation of T star. And once you have the matrix representation of T star, you have T star. You have the both. Okay? So, what does this result is telling us? So this result is telling us 3 important things. Number one, first of all, it's telling us that in finite dimension, every linear transformation has an adjoint actually. Previous case where you had the space of all polynomials over the interval 0 to 1 was an infinite dimensional space actually, okay, whose basis was this 1t and t square, t cube, and so on and so forth. Okay, so these were the bases of it. So it's an infinite dimensional space. So we saw one example that in infinite dimensional space, it is not necessary that every linear transformation must have an adjoint. But what does this result is telling us? That if you are in finite dimension and you have a linear transformation, you're always going to have an adjoint actually. Okay? The question is, can I find the matrix representation of what do you call adjoint? The answer is yes, you can find it easily. If you have the matrix representation of the, what do you call, T, beta gamma matrix representation of T, just take its conjugate and you have the matrix representation of T star actually. Okay? So these are the two important things actually. So I'm going to prove first part, and B is going to be an exercise for you to read for yourself actually. Here's the proof. Here's the proof. So let me take, say, a vector W, an arbitrary vector W from W. Okay, from W. And let me define a map phi W, a functional. Let's define a functional corresponding to this small w from W into R by R maybe F by this manner, that phi of W operated onto, say, some U, okay, some U is equal to TU W, okay, is equal to TU W. Then what happens? Then what we can show, I'm not showing it, we can show that this phi W is a functional, okay, and if it is a functional, okay, if it is a functional, then there exists by Riesz Representation Theorem, then by Riesz Representation Theorem, there exists a unique element, let's give that unique element and name S of W. Okay, let's give that unique element S of W. S of W, or maybe let's give that unique element, say, W star. Okay, such that TU W is equal to U W star for all U in W. Okay, for all U in W. So what we can do, now here's the thing, for every W I have such a linear functional, and for every such linear functional I have a W star. So in other words, I can say that for every W there exists a W star for which this is true. for which this is true. So in other words, for every W, there exists a unique W star for which this is true, and we know the W star, by the way. Okay, so we know the W star. This is not a big deal. Okay, we know the W star. So for every W, there exists W star such that this is true. So now let us define a map T star. Now define a map T star. Okay, that is a map from, so T is from V to W, so the T star, let's define it from W to V. By the way, W star will exist in V, so that this is going to be in space V. Okay, so let us define T star as a map from W to V such that it swallows a vector W, and since for every corresponding W we can find a W star and spits out what do you call W star. Okay, then this map is well defined. Okay, maybe this is a good exercise to prove that this T star is well defined. I mean, it is already well defined because, I mean, it's not difficult to see it's well defined because for every W there exists a unique output actually. So the map should be well defined. It's not difficult to check that this map is well defined. So now, since this is true, you can say that TU W is equal to U W star, but W star is equal to what you call T star W for all U and for all U in U. Okay, so this is going to be true for all U in V. So is it? This is not a linear functional on W, but it's a functional on V actually, yes. For all U and V. Okay, so you have to be a bit more careful. So this should be for all U and W, and W star is also in V, and for all U and V. So this is true. Hence, what does it show? T as a self-adjoint. T has adjoint, or hence T star is adjoint of T. Okay? By the way, since we know the description of W star, I mean, you can go back to what you call previous theorem where we proved the Riesz Representation Theorem. Just go back to it. In the Riesz Representation Theorem, we said that there exists a unique W which satisfies, such a condition, okay, and that W has this description actually. So what is the description of it? Phi of say V1 bar V1 plus up to phi W of V1 bar V1 up to phi of Vn bar W Vn. So this is really explicit definition of the T star of W. T star of W. So this is the explicit definition of T star of W. Okay. So what does this shows? This shows that if you have a finite dimensional inner product spaces, you always have a self-adjoint actually. Okay, and I am leaving this for you to do as an exercise actually. You can read it from the book, okay, and try to figure out the proof for yourself. Let's do some more finite dimensional examples of finding the self-adjoint operators. Okay. Let's do some more examples of finding the finite dimensional operator. So here is another example. In the book it's example 5.6.30. Okay. So let V, and it's an abstract example actually, even the example is abstract. Okay, so let V be a finite dimensional vector space, inner product space, and phi from V to its field F be a linear functional, be any linear functional actually. The question is that if you have a finite dimensional vector space and a given linear functional, the question is how to find the conjugate of it actually, the adjoint actually, how to find adjoint of a linear functional. Okay, this is what the next thing is. Obviously, the linear functional is going to be a map, a linear map from F into, what do you call it, the vector space. This is what is going to be the F. Okay. So what does Riesz Representation Theorem say? So since phi is a linear functional, okay, so by Riesz Representation Theorem, there exists a W, okay, in V such that what? That phi of V equal to the inner product VW in V for all V in V. Okay, so this is what is going to happen actually. Now if I use the definition of the adjoint of, what do you call, the operator. So what is the definition of adjoint of operator? So by definition of the adjoint of operators, for example, if I take, say, V phi star operated onto, by the way, phi is going to swallow scalars actually. So I'm going to put a constant C. So inner product of V with phi star of C is going to be equal to what? Since phi star is adjoint of it, so you're going to say that this should be phi of V phi this. But phi of V phi is what actually? Okay, phi of phi is what? You can write this phi of C V as, so what is the inner product? Okay, so this is the inner product in V actually. Okay, so it's phi of V, which is a vector, C times, so it's not really going to be C, so it's going to be C times the vector of 1 actually. Okay, the unit vector. Okay, this is what it is going to be. So what can I do is that I can pull this C out, so it's going to be C bar times phi of V times 1, its inner product should be equal to, what do we call